Suppose that magnetic susceptibility for the aluminium is provided to you and whose value is 2.1 into 10 to the power minus 5. The value of Km for aluminium is provided, which is 2.1 into 10 to the power minus 5. And we have to calculate the percentage increase in magnetic field. So magnetic susceptibility for aluminium is provided and we have to calculate the percentage increase in the magnetic field. Then again we use the formula percentage increase in magnetic field is equal to B minus B0 divided by B0, and this factor is multiplied by 100, which come out to be Km into 100. And for this example, Km is given 2.1 into 10 to the power minus 5. So substituting the value of magnetic susceptibility for aluminium, which is 2.1 into 10 to the power minus 5 multiplied by 100, that is 10 to the power 2, which come out to be 2.1 into 10 to the power minus 3. So this is the value of percentage increase in magnetic field if an aluminium core is inserted in the solenoid whose value is given and which is 2.1 into 10 to the power minus 5. Again, regarding this article, we take some numericals, and the first numerical is if a thin rod of ferromagnetic material, thin rod of ferromagnetic material having dimensions, the dimensions of this thin rod are given, which is 10 centimeter by 0.5 centimeter by 0.2 centimeter. So dimensions of this ferromagnetic material is given. Again, the value of H is provided. The value of H is 5 into 10 to the power 3 ampere per meter. And the value of magnetic dipole moment is provided, which is 5 ampere meter square. And in this case, we have to calculate magnetic induction B. So if thin rod of ferromagnetic material having dimensions 10 cm by 0.5 cm by 0.2 cm and the magnetic intensity is 5 into 10 to the power 3 ampere per meter and magnetic dipole moment is 5 ampere meter square. Then we have to calculate B. As we know that B is equal to mu 0 into bracket H plus mz. Today we have studied this equation. So B is equal to mu 0 in bracket H plus mz. Again, this equation can be written as mu 0 into bracket H plus mz, that means magnetization, and this magnetization can be written as net magnetic dipole moment divided by the volume. So now, by using this formula, we are going to find the value of B. So B is equal to mu 0, that is 4 pi into 10 to the power minus 7, bracket the value of H, which is 5 into 10 to the power 3, plus net magnetic dipole moment, which is 5 ampere meter square, and divided by the volume. So as the dimensions are given, 10 centimeter into 0.5 centimeter into 0.2 centimeter, then the volume of this ferromagnetic material is 10 to the power 6 meter cube. So the volume of this ferromagnetic material is 10 to the power, it is minus 6 meter cube. And if we substitute this value, M net is 5 divided by volume, which is 10 to the power minus 6. So which is again equal to 4 pi. 4 into 3.14 into 10 to the power minus 7 in bracket 5 into 10 to the power 3 plus 5 into 10 to the power 6, bracket close. Now next step is this B is equal to 4 into 3.14 into 10 to the power minus 7, and we have to take common 5 into 10 to the power 6. So common term is 5 into 10 to the power 6. So the term remaining in the bracket, which is 10 to the power minus 3 plus 1. So this is the next form of this equation. And again, the term which is in the bracket, which is 1 plus 10 to the power minus 3, which is very small, so we neglect this term. And if we neglect this term, our answer becomes 5 into 4 into 3.14 into 10 to the power minus 1, which is equal to 20 into 3.14 into 10 to the power minus 1, which is equal to 2 into 3.14 into 10 to the power 0, and which is equal to 6.28. And the SI unit for this magnetic induction is Tesla. So in this example, the value of B is 6.28 into 6.28 Tesla only. Now, the next numerical, which is based on Rowland ring, is, suppose that Rowland ring has mean radius which is equal to 16 centimeter, and the number of turns are 1000, and the value of relative permeability mu r, which is equal to 400, and the value of current is 1 ampere. And in this case, again we have to find the value of B, that means magnetic induction. So in this example, we have provided the mean radius of the Rowland ring, which is 16 centimeter, number of turns which is equal to 1000, relative permeability which is 400, and magnetizing current which is 1 ampere, and we have to calculate again the value of B. Then we use the formula B is equal to mu H, again which is equal to mu 0 into mu R into H, which is equal to again mu 0 into mu R, and the value of H is N into I. And the final form is B is equal to mu 0 into mu R into N. In case of toroid, N is equal to number of turns per unit length, that is capital N divided by 2 pi R into I. If we substitute the values in this equation, mu 0 is 4 pi, that means 4 into 3.14, or 4 into pi. Mu r is 400, that means 4 into 10 to the power 2. N is equal to 1000, that means 10 to the power 3, multiplied by current is 1 ampere, whole divided by 2 pi into r, and the radius is given 16 centimeter, that means 16 into 10 to the power minus 2 meter. All the values are substituted to calculate B. Then this pi gets cancelled with this pi. Again 4 into 4 is 16, which is gets cancelled with this 16, and therefore the remaining terms are only 1 divided by 2 into 10 to the power minus 7 plus 2 minus 5 minus 5 plus 3, which is minus 2, and this 10 to the power minus 2 go in the numerator, therefore they cancel each other, and our answer is half, which is equal to 0.5 Tesla. So, regarding with rho damping, we have taken 3 numericals of different types. Now, today we are going to study different types of numericals regarding this chapter, magnetism. So, the first numerical regarding this article or magnetism is, if the susceptibility of paramagnetic substance is capital K at 27 degrees Celsius, then at what temperature this susceptibility becomes K divided by 2. So this is the numerical. If susceptibility of paramagnetic is K at 27 degrees Celsius, then we have to find at what temperature its susceptibility becomes K divided by 2. So in this case we use Curie's law, and as we know that magnetic susceptibility is inversely proportional to the absolute temperature. Here instead of chi we use K, which is the magnetic susceptibility of paramagnetic material. So K is inversely proportional to 1 by T, and therefore we write K2 divided by K1 is equal to T1 divided by T2. This is the equation, and by using this equation K2 is given, whose value is K by 2 divided by K1, which is K, which is equal to T1, and the value of T1 is provided, which is 27 degrees Celsius. So T1 is equal to 27 plus 273 divided by T2. So K by 2 by K is equal to 27 plus 273 divided by T2. And if we solve this, we get T2, which is equal to 600 Kelvin. But as the value of temperature for chi equal to K given in degrees Celsius, T2 must also be in degrees Celsius. So T2 is equal to 600 minus 273, and which is equal to 327 degrees Celsius. So this is the answer. Now if a substance is a diamagnetic substance, and for that diamagnetic substance different alternatives are given A, B, C, D. So for diamagnetic substance, first alternative is given mu r is equal to 1.5 and epsilon r is also equal to 1.5. Second alternative is mu r is equal to 0.5. Epsilon r is also equal to 0.5. Third alternative is mu r is equal to 0.5. Epsilon r is equal to 1.5. And last alternative is mu r is equal to 1.5 and epsilon r is equal to 0.5. Then which of the following alternative is true for diamagnetic material? As we have studied, in case of diamagnetic material, the relative permeability mu r is less than 1. So relative permeability is less than 1. So regarding this assumption, the alternative B, in alternative B mu r is 0.5. Also in alternative C, mu r is also 0.5. But again, second constant is provided, that means relative permittivity of the diamagnetic material is given, which is 1.5. So for diamagnetic material, as mu r is less than 1, the epsilon r must be greater than 1. And this can be shown in analogy with mu 0 and epsilon 0, or in analogy with mu and epsilon, or in analogy with mu r and epsilon r. Or we have already studied in electrostatics the dielectric constant K, that means epsilon r is equal to 1 for air or vacuum, which is equal to infinity for metal, and for other metal is lies between 0 and 1. So the values of mu r and epsilon are provided, then we have find that which one of the alternative is correct in case of diamagnetic. Similar MCQ can be asked regarding the paramagnetic and ferromagnetic. The next MCQ is, as we have studied, the electron is revolving around the nucleus in circular orbit, and as the electron is revolving in circular orbit, it possesses magnetic dipole moment, and that magnetic dipole moment, we know that it is given by the formula m0 is equal to 1/2 in EVR, as we have already proved this in my first lecture. Then in this case, we want to show that if the electron is revolving around the positively charged nucleus, then the values of orbital magnetic dipole moment and the principal quantum number n, how these two are related with each other. So the alternatives are provided. First alternative is given, the magnetic dipole moment is directly proportional to n. Second alternative is given, magnetic dipole moment is inversely proportional to n. Third alternative is given, m is directly proportional to n square, and last alternative is m is inversely proportional to n square. So MO equal to EVR by 2, and m equal to, we have already proved, which is equal to N into E into H divided by 4 pi ME. And as we have already studied, if the value of N is kept 1, then we get Bohr magneton. And therefore, the orbital magnetic dipole moment of this revolving electron is given by the formula MO equal to NEH divided by 4 pi ME. And therefore, we write or conclude that MO, orbital magnetic dipole moment, is directly proportional to N. That means first alternative in the MCQ is correct. Again, we take one simple numerical which is based on the rod and ring. And in this case, suppose that in case of a rod and ring having mean radius which is equal to 10 centimeter and number of turns is equal to 3142. 3142. And the magnetic susceptibility is given, which is 5 into 10 to the power minus 4, and the value of current, which is equal to 4 ampere. Then, by using this data, we have to find the value of H. What is the value of H? As we know that H is equal to Ni. So H is equal to the small n in case of toroid, which is the number of turns per unit length. That means n, small n is equal to capital N divided by 2 pi r into I. And now, if we substitute the values in this formula, n is given, which is 3142 divided by 2 pi 2 into 3.14 into radius is 10 into 10 to the power minus 2, and the value of current, which is given 4. And if we solve this, we get the value of H, which come out to be 2 into 10 to the power 4 unit is ampere per meter. Then our next MCQ is, if a diamagnetic substance is placed near the bar magnet, then what happens? It will be attracted by the North Pole, it will be repelled by the North Pole, it will be repelled by the South Pole, or it will be attracted by the both poles of the magnet. So if a diamagnetic substance is taken and near that diamagnetic substance is a bar magnet is placed, then this diamagnetic substance is repelled by both the poles, S pole as well as N pole. So this is one of the simple theoretical MCQ regarding the diamagnetism. Now, in my today's lecture, I am going to take two last MCQs. So first MCQ is a graph between intensity of magnetization and magnetic intensity is given for diamagnetic substance. Suppose that the nature of graph is, so along x-axis there is H, along positive direction of y-axis there is I, also in negative direction of y-axis again I. This is origin, and we have plot a graph in which there are four straight lines, two in the upper part and two in the lower part of this graph, and they are named as A, B, C and D. So a graph is plotted between I and H for a diamagnetic substance. Then, in this graph, OA is correct, or OB is correct, or OC is correct, or OD is correct. So there are four straight lines. Two are in the upper part and two are in the lower part. It is the nature of graph between I and H, and we have to find the nature of graph regarding the diamagnetic substance. So as we know that in case of diamagnetic substance, the magnetic susceptibility is small and negative. And therefore, in the lower part of this graph, OC and OD both represent negative susceptibility, but the value of magnetic susceptibility for graph OC is more or less as compared to the OD, and therefore OC is the correct graph for diamagnetic substance. And regarding magnetism, last MCQ, a graph between magnetic susceptibility and reciprocal of absolute temperature is given. So magnetic susceptibility is taken on y-axis and reciprocal of absolute temperature is taken on x-axis. And the values are provided for chi, and the values are provided 0.1, 0.2, 0.3 and 0.4. For reciprocal of absolute temperature, values are provided 0.2, 0.4, 0.6 and next point is 0.7. And along x-axis, as we have represented the value of reciprocal of time period, and this reciprocal of time period is represented in 10 to the power minus 3 per Kelvin. So 1 by T is represented in 10 to the power minus 3 3 per Kelvin. And the nature of graph is a straight line passing through origin, and the maximum value of Km is 0.4 and the maximum value of 1 by T is 0.7 into 10 to the power minus 3 per Kelvin. And from this graph, we have to find the value of Curie constant. So find C is equal to what? Curie constant C is equal to what? As we know that C is inversely proportional to 1 by T. Or we know that magnetic susceptibility is inversely proportional to 1 by T. Or Km is equal to C divided by T. So K is equal to C divided by T. And in this MCQ, we have to find this Curie constant, that is C. So this Curie constant C is equal to Km into 1 divided by Km divided by 1 by T. So Km is equal to C into 1 by T. Therefore, C is equal to Km divided by 1 by T. The value of Km is given on the graph, which is 0.4. The value of 0.1 by T is given, which is 7 into 10 to the power minus 3. So the value of this Curie constant is 57 Kelvin. So from this graph, the Curie constant is 57 K. So dear students, in my 4 lectures, we have completed this topic by taking all the articles and extra information about other points regarding this chapter and few numericals and MCQs.